So if you take a math class here at City College and the class is before 6 p.m., so anytime before 6 p.m., not 6 p.m., anytime before 6 p.m., math classes, you will be taking a department final. So at the very end of the semester, the instructor is called on to bring his students on a big lecture. And on summer is not required, but it is optional, right, for instructors to do that. The policy for CCNY, the reason why we do this is so that there's more than one instructor, right? If anything happens, it could be any emergency that can happen, right? So they don't want one single instructor to be there and have no support. So and also when students go to the restroom, for example, someone has to escort them to the restroom and escort them back to the restroom. If it's a female, a lady, instructor will escort them. So this is very popular here in City College, where at the end of the semester, you will be taking the department final if the class happens to be before 6 p.m. So anything 6 or after, like 6 p.m. or after, you will be taking an evening exam, but in the same classroom that you usually meet up, right? And so yesterday, our final exam looked like this, and where 4 instructors or 3 instructors brought their students in. We just put them in a lecture hall, and this is how they are here. So you can have an idea what at the end of the semester will look like in a regular semester. And in a regular semester, you will be assigned a seat. You will be sitting in this row in this specific seat, and this instructor, if he's not there, any instructor will know exactly who's sitting there, who's supposed to be sitting there. And usually at the end of the semester, they check IDs in the final exam, one by one, making sure that you are on the right seat, taking the right test, right, and so on. It has happened in the past that students take exams for other students, and that was a big issue. They started to adopt new policies and so on. Just to give you a glimpse of that. So also, we're gonna go over the quiz. We haven't gone over any quiz. Today's quiz, right? We're gonna go over it together in here to see how you answer these questions. And where I type the quizzes, right? We in mathematics type our materials using a software. It is very common to do that for mathematics. For example, we use a software called LaTeX, and it looks like this, right? Where you are commanding every single one of those things, and what it will do is it will create a PDF on the right side. But the advantage of doing this, if you want to do or add any graphs or anything, you can easily input it here, and it will output the graphs in there. So it's very it's very nice to do this. Also, if you want to create an animation, you can do this, but you can't print it out as a PDF. You can just clip it, yeah. But just know that it's really nice when you do this, because you are getting familiar with how commands or codings work, and it has an advantage of doing all of that. So anyways, let's go over the quiz, right? So today we took quiz number 7. Let's see how we will answer these questions, right? So for number 1, you had 2 parts, part A and part B. Find the coterminal angles for each of the following. Coterminal angles are angles that have the same terminal point. They end exactly at the same ending, right? And we usually are looking for a coterminal angle between 0 and 2 pi, right? If it's too much more than 2 pi, we want to cut that angle down. If it's less than 0, we want to cut that angle down again. And so 19 pi over 4, right? 19 pi over 4. Let me do this this way. Okay, that's better. So we are going to say, what is 2 pi here if it has a denominator of 4? 8 pi over 4. So plus 8 pi over 4, these will be 16 pi, and we still need 3 more. So these will be 3 pi over 4. So our answer will be that the coterminal angle to 19 pi over 4 will just be 3 pi over 4. when you look at this mathematically, right, how can 19 pi over 4 be equal to 3 pi over 4? They're not equal, but mathematically they are equal in the sense that if you look at the clock, for example, right, if you add 12 hours to it, it will come back to the same time. So we call this in mathematics, every time that has a cycle or it behaves like a cycle, we call this modular. Modular will be the right word for it. But 19 pi over 4 obviously is not equal to 3 pi over 4, but 3 pi over 4 has the same terminal point as 19 pi over 4, the same ending, right? And so what about for B? Negative 800 degrees, between 0 degrees and 360. We are going to add 360 degrees. So we start off with negative 800 degrees. We add, so let me do it like this. We're going to add 360 degrees. And what is that going to give me? 440 negative, right? And that's not good enough, so we add another 360 degrees. And what is that going to put me at? Yeah, negative 80. And that's not good enough, so we add another 360 degrees. And what is that going to put me at? 280 positive, right? And is that between 0 and 360 degrees? Yeah, so that will be my answer. None of the answers before were good enough, right? But the negative tells you that you're going clockwise instead of counterclockwise, starting from the positive x axis. So that's that. That's number one. What about number two? So convert each of the following, right? So 5 pi over 3, you want to convert that from radians to degrees. So we're going to multiply, right? So 5 pi over 3. Yeah, so 180 degrees over pi. And what will happen to the pi's? Cancel out. So you have 5 over 3 times 180 degrees. And 180 divided by 3, 60. 60 times 5, 300, yeah. So your answer should be 300 degrees, like this. Like that. At the end, I decided to add 5 extra minutes because they had parts, A and B, and I thought maybe that was tedious. So, yeah. So, and plus I wanted to know whether you knew the answer, right? And eventually you will get it, right? Maybe if you needed 1 extra minute to finish up, right? And what about B? 300 degrees, you want to convert it to radians. Sure.
So, since we are looking for so can we again go again, like can we do 360 minus 280? Can we do that?
Can we add another 360 or subtract?
Can we do 360 minus 280? We can do that.
Yeah, but if you do that, right, you're gonna get positive 80 degrees, right?
Positive 80, but in between 0 and
Yeah, but positive 80 is gonna be here. Look, 80 degrees is gonna be somewhere over here, right? 80 degrees, right? And what we're saying is that that's not the terminal point that we want. 280 will be here. That's the right one. So this is the right angle right here. This one. It should end in the fourth quadrant. 80 degrees ends in the first quadrant.
80 would be the reference.
Yeah, so 80 degrees will be what we call the reference angle. Yeah. So it has exactly the same ending. It has to have the same ending. Yeah. But hopefully there's a big difference between 80 degrees and 280 degrees. They don't end in the same quadrant even, right? Yeah. So let's take a look at 2b. So you want to convert 300 degrees to radians, right? So 300 degrees, and if you want to convert this to radians, well, you already did that conversion right here, right? And if you notice that, you can just write out the answer. So if you didn't notice it, you will multiply this by pi over 180 degrees, and you'll get 5 pi over 3. So if you only wrote 5 pi over 3, I will understand where you get this from. Yeah, I will say, okay, the person just noticed it, that it came from here. Right? So that's good, right? Reasonable. So number 3, right? Find the radius r of a circle if an arc of length 5 meters on the circle subtends a central angle of pi over 2. So we have an arc of length, is going to highlight that, an arc of length 5 meters, right? This one right here. An arc of length of 5 meters. We're going to use not the area formula, but the S equals R times theta, theta times R. Right? And in this case, we know that the arc length is 5. We don't know what the radius is R. And theta is pi over 2. It's already in radians. If it was in degrees, we will have to convert it to radians. So it's pi over 2. And what is R going to equal to then? 10 over pi? Yeah, that's good. That will be
Is that the same as 10 over 1 times pi?
10
Over 1 times pi.
over 1 times 5 like this? Pi?
No, over 1
Times pi? Yeah, it's the same thing.
Okay.
Yeah.
Can you scroll up for a second? Can you scroll up?
Higher? Yeah.
Like about B, like yesterday I do based on what you say. So as you can see, 280 is on the fourth quadrant. So since it's on the fourth quadrant, we can do 360 minus 280. Like we are allowed to do that.
To get the reference angle. Yeah. To get the reference angle, yeah. But not the coterminal angle.
10 over 1 times pi. That's the same.
Yeah, so if you wrote 10 over pi, that's correct. 10 over 1 over pi, right? That's the same thing. You can just do this, right? Right. Yeah, 10 times the reciprocal of 1 over pi. Yeah. But this is the answer, 10 over pi. For number 4, you have find the area of the sector of a circle with central angle 12 degrees if the radius of the circle is 3 meters. So now we're going to use the other formula, right? Because this one tells you the area of a sector. So what is the formula for this one now? A equals to theta. And somehow you saw that in the days, but it's hard to remember these little formulas. So you learn techniques on how these formulas came about. Maybe in a year, you don't remember the area is 1/2 r squared times theta. You don't. But you remember how we figure it out by a ratio, and you can work it out yourself. It doesn't take too long, and that's what you want to be able to do. That's learning. Memorization is good enough for a semester, but after that, it's not good enough. In calculus, you're going to see this formula again, but we're going to use it in a different variation of this to figure it out areas that are not from perfect circles. They're arcs, right? But not perfect circles. Like the graph that I showed you last time, right? The areas were those things, like beautiful shapes, like petals of a clove, right? And so on. So A equals to 1/2 r squared theta. What do we know? We know that the central angle is 12 degrees, right? But 12 degrees, we have to convert this into radians. So we multiply this by pi over 180 degrees. And the degrees will cancel out. So we have 12 divided by 180. So you can divide them by 6 if you want to. So 12 divided by 6 will be 2. And pi and 180 divided by 6 will be 30. Right? And now you can even simplify this a little bit more. Pi divided by 15th. Yeah. If you got to that, that's great. Otherwise, you have to simplify it later, right? So let's plug this into here. So the area will be equal to 1/2. The radius, you're given that the radius is 3 meters. And theta, now we convert this into radians and is pi over 15th. So all of these, right, is 1/2 times 9 times pi over 15th. And you have to simplify this, right? So 1/2 times 9 times pi over 15th. So what is this going to simplify to? Right. So 3 pi over 10th, right? The 9 and the 15 have a 3 in common. Yeah, so you cancel them out.
Isn't there a way to do it without converting?
But the area here is not going to be measured in degrees, right?
No, but like, there's another way.
Did you get the same answer?
Yeah.
Okay, then it's good.
Would you mark it wrong if you didn't simplify?
It's just that you want everything to be simplified at the end, right? So maybe if you didn't simplify it, it depends on how the TA grades it, right? They might just circle it and they write a reminder here. Don't forget to simplify it, right? In the final exam, you really want to write the answer in simplest terms all the time. Sometimes proofs in mathematics depend on the ability to simplify things. Like the square root of 2, why is it irrational? Why is it? Because it cannot be expressed as a fraction, but not just any fraction, as a simplified fraction. Yeah, and it's really is a key thing that any fraction can always be expressed in simplest terms, right? But so that's the answer. If you wanted to know the units for this area, the units for the area will be meters squared, and the radius up there before the radius for that one would have been measured in meters, right? According to the units in the problem. But again, we wouldn't be mindful of these units, right? But just keep in mind that there are units next to it. So number 5. So let's speed this up, right? Sine of pi over 4 is radical 2 over 2. Cosine of pi over 6 is radical 3 over 2. Tangent of pi over 3 is radical 3 over 1 is just radical 3. And cosine of pi over 3, 1/2. So all of these is just going to be radical 6 divided by 4 minus radical 3 over 2. And you can leave your answer like this. If you want to combine this into a single fraction, it will be radical 6 minus divided by divided by 4, like that. But it's your choice to express it as a single fraction or not.
Sir, can we leave the answer in the first step?
Yeah. What do you mean though?
The first step.
This one?
Yeah.
But you can multiply radical 2 and radical 3, right?
I know, but like, can we leave it like that?
It's try to simplify it as much as possible. Yeah. If you can multiply radical 2 and radical 3, why not multiply them out?
So are they gonna take up one for not multiplying?
Probably, yeah. Because after you multiply, what will happen if you had this, like radical 6 times radical 3, and you leave the answer like this, right? But radical 6 times radical 3 will give you radical 18th, right? And then you can simplify that, right, into, 3 radical 2. So things like that can be simplified after you multiply them out, right? Sometimes it's obvious that you can do that, sometimes it's not, right? But you should always try to simplify things out, right? So here is number 6, right? Number 6. Find the exact value of these trigonometric functions, right? So A, you had sine of 23 pi over 4. So what are we going to do? First find the coterminal angle, and then find the reference angle. So let's see if we can do this, right? So 23 pi over 4. So we're going to go by 2 pi's. Yeah, so it's 8 pi over 4 plus 8 pi over 4. If you add another 8 pi over 4, that's going to give us
24, 7.
Yeah, we can't do that. So that will be 7 pi over 4. So this is equal to 23 pi over 4 is equal to 7 pi over 4. And this is not the reference angle. This is the coterminal. Yeah, at least it tells you which quadrant this is on. This is the third quadrant. So now that we know that it's in the third quadrant, so this one right here. So here is x and here is y. Now that we know that this is in the third quadrant, we want to find the reference angle, right? And so this angle right here is in quadrant is in the fourth quadrant, right? Yeah, quadrant 4, I believe so. Yeah. And now that we know that it's in the fourth quadrant, we want to find these angle right here, which is the reference angle, right? Reference angle. And because we know that it's in the fourth quadrant, to get this, it's 2 pi minus
7 pi over 4.
Yeah. So if you do that, that's going to give you pi over 4. So in other words, we are going to start off with this logic. Sine of 23 pi over 4 will be equal to sine of the coterminal angle, which is 7 pi over 4. Now, 7 pi over 4 is in which quadrant? Fourth. So it will be negative. So it will be negative sine of pi over 4, the reference angle. And sine of pi over 4 is radical 2.
2 over 2.
So it will be negative radical 2 over 2. Like that. Yeah.
How did you go from the co-terminal that was going to be the fourth quadrant?
Yeah, so I showed you this technique last time. So when you are here, what is the angle when you're up there? Pi over 2, yeah. So you want to have the same denominator, or sorry, let me see. You want to have the same, so pi over 2, you want to have the same denominator as the coterminal angle, which is 4. So you multiply these by 2 over 2. So pi over 2 will be expressed as, 2 pi over 4. Now, what about pi? 4 pi over? Yeah. And what about 3 pi over 2 on the bottom? 6. And then 2 pi, in the positive x-axis, 2 pi all of a sudden will be? 8 pi over 4. Now it's easy to see that, right, the coterminal angle is 7 pi over 4. 7, just look at the numerator, 7. So this is, the numerator is 2, 4, 6, and 8. 7 is going to be here, 7 pi over 4. So you know that it's going to be on the fourth quadrant. So if you ever want to know which quadrant it is on, you shouldn't convert it to degrees. That will take a little bit longer. You can just write down the same denominator as that one, the common denominator. So in this case it's 4, 4, 4, and it's easy to see that 7 pi over 4 will be between these guys, 6 pi over.
How is it negative sine pi over 4?
Like, how?
Yeah, like how did you get negative sine?
Like, which step does it? Yeah, so these are the steps here. Right. Which step doesn't make sense?
The last one, it says negative sine times pi to the power of 4.
Yeah, the last step doesn't make so do you does it make sense why we have this one right here?
Yeah, I do understand, but why did you put a negative sign there?
There was a negative where I circled the expression here. You see where I circled this right here?
Yeah.
There's a negative there in front of it.
But why there is a negative?
Because 7 pi over 4 is in the fourth quadrant. Sine is negative in the fourth quadrant. Yeah. 7 pi over 4 is in the fourth quadrant, and sine there will be negative. It doesn't make sense? So 7 pi over 4 is in quadrant 4. Sine there will be negative, and that's where the negative came from. Right? What about the next one? Right? Let's see.
Bring the negative sign out.
And somehow students feel more comfortable with degrees, right? At this stage. Later on, they will feel more comfortable with radians. Is the thing to be familiar with. So if this is a transition that you have to go through to convert to degrees to understand something, you can do it at this stage, but you have to get comfortable with radians. It's better. So cosine of negative 240 degrees. These will equal to cosine of positive 240 degrees. Yeah, so cosine, if you have a negative inside, it wouldn't matter. The trick that I told you yesterday is that cosine of negative x. Yeah. So why put a negative when it wouldn't matter whether you put it positive or not, right? So because cosine is even, right? Like a parabola, if you put positive 2 or negative 2, it wouldn't matter because the parabola will be even. So now, 240 degrees, right? Which quadrant is it on?
It's in the third quadrant.
Yeah, third quadrant. So here is the picture that we have. Right. So here, and in degrees, it's really easy to tell which quadrant the angle is on, right? Yeah. So this is 240 degrees, right? So quadrant number 3. And what is the reference angle in this case? The reference angle will be this little gap right here.
30.
Yeah. So we're gonna do
60.
240 degrees, right?
Mhm.
Do you agree that if you find the coterminal angle, right? What will you find that the coterminal angle of 240 is 240 because it's already between 0 and 360. So we wouldn't start by doing that sorry, 340 degrees.
Because degrees are negative though, it doesn't mean it's going the other measuring.
Yeah, but again, having an input of negative 240 or having a positive input of 240, it wouldn't matter for cosine. So if you start with a negative, you can go clockwise, right? But in this case, I'm first ignoring the negative.
We're at the same reference.
Yeah, so I wouldn't want to go clockwise. I can just use the positive. It would have the same result for cosine. It wouldn't matter. So 240, not 340. 240, this one, because it's already between 0 and 360. Now the reference angle will be what now?
60.
Yeah, this will be 240 degrees minus 180 degrees, and that will give me. Is it 60 degrees?
Yeah.
Yeah. Now, which quadrant are we on? Third quadrant. Cosine there will be negative. So we say that this cosine of negative 240 degrees will equal to cosine of positive 240 degrees, because it doesn't matter for cosine, which will equal to negative cosine of 60, and cosine of 60 will be, yeah, so this will be negative 1/2, like this. Now, if you go to a calculator, right, which we won't do that in an exam, but if you do go to a calculator, right, and say, let me check this, right, here, let me take this out, yeah, there you go. So let's put cosine of 240 degrees, right, like this. Let's put positive first. What did it give us? It gave us negative. Let's put negative inside of it. I'm telling you, it doesn't matter because cosine is even. Ouch. Cosine is even. So let's see. There we go. There's a negative, and I enter this, and this is what tells me that cosine of negative 240 degrees is, yeah, negative 1/2. It's the same exact thing. It doesn't matter whether you put positive 240 going counterclockwise or negative 240 going clockwise. It wouldn't matter, and this is what the little sign gives you, that it went clockwise. And if you go clockwise, you end up in the third quadrant. Cosine is negative there as well, so you don't get a different result. You get the same result. You don't get contradictions like that, right? So now, that's where we are right now. So for seventh, the reference angle now, right? So 3 pi over 4. So which quadrant is this on? 3 pi over 4.
In the second quadrant.
Yeah, second quadrant. Yeah. So pi will be 4 pi over 4. That's less than 4 pi over 4. Yeah. So this here will be somewhere in the middle there. So this is in quadrant 2. And the reference angle for this one will be somewhere over here, right? Yeah. So the reference angle, what would it be now?
Pi over 4.
Yeah.
4 pi over 4 minus 2 pi.
Yeah. So let me write it like this first: pi minus 3 pi over 4. So that will be 4 pi over 4 minus 3 pi over 4, right? And this is just going to be pi over 4. Yeah, like that. There you go. So it makes sense. What about 310 degrees? Which quadrant is it on? Fourth quadrant? Yeah, correct. So here is y and here is x. And this is where we are right now. 310 degrees. This is in quadrant number 4. And the reference angle for this one will be this missing gap over there, right? So the reference angle, yeah, perfect. So it's 360 degrees minus 310 degrees. Yeah, that's 50 degrees. So that makes sense. Yeah, and again, with degrees is much easier, right? We are able to visualize things, but you have to get comfortable with radians. You have to, yeah, right? So the good thing is that you can always convert radians to degrees, right? And then figure out the answer in degrees, convert back to radians, but that's too much of a transition. Yeah. So 8. The angle of elevation of a tall building is found to be 15 degrees from the ground at a distance of 2 kilometers from its base. Using this information, find the height of the building. You may leave sine, cosine, or tangent in your final answer, right? So here is the building, It doesn't matter where it is, right? So here. There you go. And there is a tall building. Say the angle of elevation, right, from the ground, right, maybe somewhere over here. Right, the angle of elevation will be something like this, right? Theta. What is theta equal to? Yeah. So this is the angle of elevation. This other angle over here, up here, this guy here, that's not the angle of elevation. Yeah, we call that the angle of depression. You probably saw this in the homework, right? Yeah. So just know that this is what we call that. Usually is this guy, right? You can also call this angle of depression if you want to. Let me see. This guy here. Come on. Yeah, this one right here. You can always also call this the angle of depression as well. Depends what reference they're using it from, right? But anyways, the angle of elevation will be on the bottom, right? And so the height of the building will be this one right here, right? Height. We should call that height H, right? Height. Did I spell height correct?
Yep.
Yeah, okay. Yeah. So the height will be equal to what? Well, the distance between the bottom point and the top of the building will be 2 kilometers, right? 2 kilometers
I thought it's.
from the ground.
Yeah,
It's from the
because it's
ground.
a front space.
Yeah. So should we just call that the height of the building? No.
The 2 kilometers is.
No, it's like the.
It's on the
base.
Uh-huh.
2 kilometers.
Oh, okay. Yeah. You guys are correct. Yeah. So the 2 kilometers will go here, right?
Yeah.
There we go. From the base of the building, right? From its base. Yeah. So this is 2 kilometers. Okay, that's perfect. Now instead of using sine, I'm going to use tangent, or I can use tangent will be better, right? You can always use cosine. You can always use that. But let's use tangent, right? So what is tangent theta equal to?
H over 2k.
Yeah, h over 2 kilometers, right? But what does that mean for h?
H equals 2 to the 10 theta.
Yeah, and theta, we know that theta is, yeah. So that will be the height of the building, right? And we are leaving our answer in terms of tiny theta. It will be really hard for us to express it using sine because we'll be missing the hypotenuse, right? We'll be missing this, right? And so if you want to use sine, you have to know what that question mark is, and that question mark will depend on h itself, right? So it will be hard to do that. This angle right here, this is a 90-degree angle, assuming that, right? And what about the angle up there? Yeah, that will be 75 because the angles in a triangle will add up to 180. So you can also use that as well, that other angle. So you could have expressed your answer using the 75-degree angle if you wanted to, right? But this is more common. You guys know why the angles in a triangle add up to 180 degrees? This is a little like why does the angles in a triangle add up to 360 degrees? The idea would be that if you draw any triangle, right? If you draw any triangle, let's just go like this. So yeah, what we do, and it doesn't matter. There's no right angle here, right? No right angle. What you do is we're going to use any one of the bases as a reference, right? So use this one right here. Well, you can't see the color. This one, right? Hopefully you can see the color. Can you see the color? Yeah. So use that as a any one of the edges would have done. When you draw at the peak, at the vertex, at the top vertex of the triangle, you're going to draw a line parallel to this one, like this. It's parallel to this, right? And there. And now what you do is take a look at this angle right here. This angle right here. Will you assume that these will equal to this angle here?
Yeah.
We call them alternating angles, right? And you will also say, hey, what about this one right here? Do you see that this will equal to this one? Yeah? And what will happen if you add and this is the funny thing, right? What will happen if you add this angle plus this angle plus that angle over there? 180. And that's exactly where the formula will come from. This is already one angle of a triangle, right? Right? And then you're adding the other angle, which is the same thing as the bottom angle of the triangle, and then the other one. So adding all the angles in the triangle will add up to 180 degrees. It's a really nice thing to think about why, right? In mathematics, every time they give you something is why. Why is a big question. It's like, so ninth, evaluate cosine of 29 pi over 6. Right? So we will need to find the coterminal angle first. So 29th pi over 6. So we're going to go by 2 pi's, right? In this case, it will be 12 pi over 6. We have another 12 pi over 6. That will give me 24 pi over 6. So what do I need? I need 5 pi over 6. And so these equals to 5 pi over 6. The coterminal angle is this one, coterminal. Which quadrant is this coterminal angle in? Second? Right? Is not in the is less than 6 pi over 6. So this is the picture that we should have here. Is it clear why is it in the second quadrant? Yeah. So here is x and here is y, and here is 5 pi over 6. So it's in quadrant 2. And what will be the reference angle in this case here? This. Yeah. So reference angle is 5 pi over 6. Sorry, is 6 pi over 6, right? Which is pi minus 5 pi over 6, and this reference angle will just be pi over 6, right? It turns out that the reference angle, if it's in radians, is just that pi over 6. You already see that from the very beginning. All you need to know is the coterminal angle to determine which quadrant is it on, right? Degrees is not as easy as that. You have to figure out which quadrant it is on and then subtract to see what the reference. But if you're given an angle in radians, it's really easy to see whether the reference angle is from the very, very beginning. But you still need to figure it out which quadrant is it on, right? So now we still have to evaluate cosine of 29 pi over 6, but that's just going to be cosine of 5 pi over 6. And is it going to be positive or negative now? Negative cosine of pi over 6, yeah. Negative cosine pi over 6, which is negative radical 3 over 2. Yeah. And yeah, in quadrant 2, cosine there will be negative in the second one. Yeah. All right. So number 10th, the last one. So if you see, I already fixed this in the problem here, right? So you sketch the graph of the function 2 minus log base 3 of x plus 3 using transformations. You state the domain and range and label all intercepts and the vertical asymptote. So for this one, if you started with the vertical asymptote, right? Vertical asymptote. Yeah. Do you guys see why the vertical asymptote will be the line x equals negative 3? Yeah. The line x equals negative 3 is the line. That's the line. If it's not clear, ask and I'll tell you. Okay? All right. So let's go over the x-intercepts and the y-intercepts, right? So let's find the y-intercept. That's easier, right? Y-intercept. So for y-intercept, we set x equal to 0, right? If you write x equal to 0, let me write it like this. X equal to 0. What does that mean? That y will equal to 2 minus log base 3 of 3. What is log base 3 of 3?
1.
That's 1. And 2 minus 1 will be equal to?
1.
Yeah. So y equals to 1. So that's the y-intercept, right? What about the x-intercept?
6.
The x-intercept, we set y equal to 0. And so we have 2 minus log base 3 of x plus 3 equal to 0. We get 2 equals to log base 3 of x plus 3, like this. And what does that mean? That you can write this?
Where it equals x
Yep. And if you write this in exponential form, it becomes a little bit easier. Why, right? There we go. So what does that mean in exponential form? That 2 to the third, right, is equal to x plus 3, right?
3 to the second.
3 to the second, yeah. Thank you. 3 to the second. Is it clear why did we get that exponential equation? Yeah. And how do you solve for x?
Just make 9 equals x plus 3.
Mhm.
Subtract 3.
So x is equal to 6, right? So that's the x-intercept. But we get these through the equations here. And now with these, you have a lot of information. A lot. You can already start seeing what this is. But I still want you to do this right here. What is the original function? The original function will be log base 3 of x. What will you say the first transformation will be?
Be around the x-axis.
Yeah, reflection
X-axis.
over the x-axis. What will you say the second transformation will be?
2 to the left. 3 to the left.
Yeah. Yeah, shift 3 units to the left. And it doesn't matter if you chose the one, right, the other one. What about the third one?
2 up.
Yeah, 2 units. Yeah, up. There we go. Now we have this. This is gonna make sure that we understand this a little bit better. And here is the sketch that we will have, right? So it will look like this. So here's x, here's y, and we started with the vertical asymptote at x equals -3. So here's 1, 2, 3, -3. So this is where the vertical asymptote is going to be on. And I had like, okay, I'm gonna move this to x equals -3, and then I'm going to do this. There we go. That's the line x equals to -3. Now, the y-intercept, what did we say the y-intercept is?
0.
Yeah. So the y-intercept will be 0, 0, 1, right? Yeah. 0, 1. Yeah. So it will always be there, right? Let me put this in this color here. What about the x-intercept?
6.
Yeah, at 6. So is it 1, 2, 3, 4, 5, 6? There we go. Just imagine that. 6. And so how is the graph going to look like? At x equals -3, will it be from up there or from below?
Will be point
From up there, right? So it will start looking like this, right? So it will come from all the way up there and slowly, right, pass through this point.
2, 2, right?
Yeah. What is it?
2, 2.
Yeah, it will pass through what do you mean 2, 2?
No, I mean -2.
Yeah, -2, 2, yeah. So these will be going something like this. There we go. And did I say to you that the log function, right, the original log function decreases really slow? It looks like it's going to settle to something, but it never. It just keeps on growing like that, right? And question?
So when finding the y-intercept, how would that look like if you would put that in like exponential form? Because I tried doing that.
Well, we don't have an exponential form for that because all you need to know is y log base 3 of 3 equals 1, right?
Would that always be the case?
Yeah. So if you want to make it a rule, you can say log base a of a always equals to 1. If the input is equal to the base, right? A.
Inverse function.
Yeah. Yeah. So log base a of a will always equal to 1. So every time you see log base 3 of 3, that will be always equal to 1.
But like when we're finding the y-intercept, would it always be like that?
Well, it's something that a log that you can evaluate, right? Yeah. And if not, you leave it like that. You leave it in terms of log. Like, for example, if it was log base 3 of 2, you just leave it like that. If it was log base 3 of 1, that would be 0, right? Yeah.
So we wouldn't like add 2 to y and put 3 to y to
No, we wouldn't. Yeah.
do that.
Mm-mm. Yeah. So this is a number, and that number here is just 1, right? Uh-huh.
Can you explain to me again how you would like
Yeah, this step right here. Yeah. So we had this. Imagine that you have log base a of some expression, right? Call it b equals c. This has an equivalent equation and in exponential form, right? The exponential equation for this one will be a to the equals b, and that's exactly what we applied here, where we have 2 as c equals log base 3, which is a here, and x plus 3 is representing b, that expression, right? All we have to do is rewrite it in exponential form. But I just followed that setup from before. These are equivalent. This is a log equation and exponential equation. Yeah, but they come from these. Right? So let me label these out, right? So I don't lose any points. So here is 0, 1, and here is 6, 0, like that. And if you want to add an extra point, that would be great, right? So for example, what would you get when you plug in -2?
2.
Yeah, you should be able to get 2. 2. Not from the graph, of course, that would be great, yeah. But if you had the original function, this function right here, and plug in -2 into x, what are you going to have? Log base 3 of 1, and log base 3 of 1 will be 0. So you're just going to get 2 out there, right? And so whenever I sketch something, I try to always plot 3 points. It's the rule that I use, right? 2 points is good, but 3 points is even better. And let's say the domain. What would be the domain for this?
Well, -3 you would
Not including -3. And the range?
all real.
And you can just write it like that, all real numbers. And so we label all the intercepts, and we also, that was bad. We also labeled or indicated where the vertical asymptote is, right? As clear as possible. Right, so let's start off with a new section. We introduce it, and then we take a break, right? Yeah.
For number 6,
Okay.
remember you said that negative or cosine will always equal positive cosine? So I remember that, and I put positive 12.
Positive what?
Positive 12, because so negative cosine of negative 240 would be cosine of 240, and I did everything, and I put in positive 12. So when you did it,
What do you mean? Positive what?
positive 1 over 2.
No, but again, the inputs, having a positive input or a negative input inside of cosine, you get the same output. The output can be negative. Yeah, the output can be negative. In fact, it is a good statement to remember. If you're plugging an obtuse angle, somewhere between 90 and 180, cosine there will be negative. Like 240 is obtuse, right? You're putting in but you can think about it like that if you want to. Yeah, sure. So every time you put an obtuse angle, right, cosine will be negative. And every time you put an acute angle, cosine there will be positive. And that's how later we determine whether two things are like this or they're opposites. Dating sites, for example. Dating sites, they can determine by the answers of the questions that you do, like 1 to 10, how will you rate and such and such. We are able to compare people that are the compatibility between two individuals, whether they're really, really close or they're far apart from each other, right? So just imagine, mathematically we can do that. We can figure it out, the compatibility, if they're pointing, right? If the angle between them, for example, right? It's really, really like an acute angle, and it's really, they're very compatible, right? Like this. But if the angle of them is almost the opposite, the answers are opposites of each other, then that will be mathematically an obtuse angle, and they're opposites, right? That's as far as they can point from each other, right? Yeah, and if they're 90 degrees, that means that they're not good enough, right? But you'll just understand that everything has a meaning in mathematics, even that, for example, right? In taxes, they always also use a compatibility. How much money you make versus the taxes that you pay, you have to be correlated, right? If you're not paying that specific amount of taxes, they can figure it out at the end of the year. You have to pay more, right? If you're paying more, they will give you some money back, right? And so on. It has to be in a specific inclination, yeah. But yeah. So today we're gonna start off with section 10.1. And section 10.1 right here, is going to be systems of linear equations. Systems of linear equations. So here's an example, right? Here's an example. Suppose that you're solving for something like this, right? Solve the system of equations, and you're given to the system like this: x minus y, for example, equals to 1, and 4x plus 3y is equal to 18th. Just as an example, right? You're solving for one particular x value, one particular y value that will solve this system. And you cannot find two solutions for a system like this. You may find, there are three options, right? You can either find no solution for a system, you can find one unique solution, or you can find infinitely many solutions. But you can never just find two solutions. Not for a linear system. A linear system is representing lines, the intersection of two lines. If you represent a parabola and a line, the intersection will probably meet at two different points, right? But for two lines, they either don't intersect, they intersect once, or they always intersect. They overlap each other, right? So there are only three possibilities for this one. We are worrying about the possibility where there is one solution, and that's what we are worrying about here. So how do you solve for this one? Number one, we can do a substitution method. Substitution. So take a look at these system again, right? I'm going to copy this. Here. Copy this. Now, take a look at these variables. So I'm going to highlight them out. This one right here is the first one. This one is the second one. And take a look at this one right here. And this one right here. Between all of those four things that I highlighted, well, highlight this a little bit more. You will solve for the easiest one. And hopefully you will see that the easiest ones will happen in the first equation. And you can either solve for x, the x variable, or the y variable in the first equation. Which one do you want to solve for? Let's solve for x. It's very, very simple. So I'm just going to start by saying, note that this is very, very easy to solve for. We'll solve for this one. This one. Yeah, we'll solve for this one. So in the first equation, we have x minus y equals 1. What does that mean for x? Yeah, or y plus 1. It doesn't matter. Yeah, that's good. Now we know that x is equal to y plus 1. We're now going to plug this into the second equation. And the second equation here, right? We have 4x plus 3y equals to 18th. Now we can replace x, right? Yeah, into there. And what is that going to give us if we replace that x into that? 4 times y plus 1 plus 3y equals to 18th. Because we know that x is equal to y plus 1 from the first equation, we use the other equation, the second equation, and replace what we know. This will be 4y plus 4 equals to 3 plus 3y equals to 18th. We can combine like terms. We get 7y plus 4 equals 18th. And what does that mean? That 7y is equal to 14, and y will equal to 2. So now we know the value of y, but that's not enough. We still need to figure out the value for x. To find x, we already know that x is equal to y plus 1, since we solved for that, right? And what replacing y with 2 will tell us that x is equal to 3. So our solution will be this: x equals 3 and y equals to 2. Or you may even write it like this. You may say that, yeah, the solution will be a point, x comma y, so 3 comma 2, for example. That could be your solution. Just one specific point where the x is equal to 3 and when y is equal to 2. That method is called the substitution method. And hopefully you have seen this before, right? The second method will be an addition method. We call that the addition method. So number 2 is the addition method. So what I'm going to do is I'm going to start off with the system of equations here. And now I'm going to take a look at 2 things only. I'm going to take a look at this side right here. Or I'm going to take a look at this side right here. Yeah, so I have 2 things that I'm looking at. I'm not looking at the variables individually. Right? Or like as before, I was looking at each of them, x, y in the first equation and x and y in the second equation. I'm looking at these. Which one do I want to cancel out? Do I want to cancel out the x variable in both equations or the y variable? It doesn't matter. So you want to cancel out the y?
It's negative.
Yeah, it wouldn't matter. Yeah. So say you want to cancel out the y variables. So now if you want to cancel out the y variables, right? This one's, ouch. Let me put this one right here. If you want to cancel out the y variables, you want to get a common factor. The coefficient for the first y in the first equation will be 1 or -1. It doesn't matter. In the second equation, the coefficient there is 3. What is the common factor between 1 and 3? 3. So you multiply the first equation by 3, and the second equation is already 3, right? So you multiply by 1. So imagine this. The first equation, you're going to multiply this by 3. And if you do that, you're going to get this system of equation. You're going to get 3x minus 3y equals to 3. And the second equation, you will multiply this by just 1. And you will do this because you don't need anything else. You don't need to. You already have a 3 next to a y, right? So what are you going to get here? 4x plus 3y equals to 18th. Do you see that your intent was to cancel out the y variables? And can you just add them?
Yeah.
Right? If you add them up, negative 3y from the first equation plus 3y in the second equation, that will just cancel out. And so you get what you want here. So if you add them up, we call this the addition method because of that. 3x plus 4x will give me 7x. And then the 3y's will just cancel out, right? And I'll get 20. So I get x is equal to? 3. So now, 3. So now that I know that x equals to 3, I can use either the first original equation or the second original equation. So I'm going to use using the first equation. Right? The first equation is this. X minus y equals to 1. Right? But what do I know about x? 3. So I get 3 minus y is equal to 1. And so I have negative y equals to negative 2. So y is equal to 2. I get exactly the same answer. I get that the solution for this one is exactly the same thing. Exactly the same results. I'm going to show you another method after we come back. But let's take a 20-minute break. It is now 10:35. So we're going to come here at 10:55, right? 20-minute break.